Welcome back. So we're looking at derivatives of inverse functions. All right, so we have a positive inverse function, so f of g of x equals x. If we take the derivative of both sides, we have f prime of the g of x, so the inside. So we have, notice the inside doesn't change, and then we have to take the derivative of the inside. So it's the derivative of the outside times the derivative of the inside, and that's the chain rule. All right, so that gives us g prime of x equals 1, because the derivative of x is 1. And then if we solve for g prime of x, we get g prime of x equals 1 over f prime of g of x, where f of x and g of x are going to be inverses of one another. All right, so in other words, if we have a function y equals 2x plus 3, we're just going to take the reciprocal of the derivative to find the derivative of the inverse. So the derivative of 2x plus 3 is just 2. The derivative of the inverse would be 1 over the derivative of the function. So that means that the derivative of the inverse is 1/2. So the beauty of this formula is that we don't need to actually determine g of x to find the value of the derivative of a point. We simply use the reflection property of the inverse function. The derivative of the inverse function at a point is the reciprocal of the derivative of the function at the corresponding point. You just have to switch x and y for the inverse. All right, and just to prove it a little bit. All right, so we have y equals 2x plus 3. If we find the inverse of that, all right, we have y equals 2x plus 3. Some random dots there just stuck. Y equals 2x plus 3. To find an inverse of a function, you switch x and y and solve for y. So this would be x equals 2y plus 3. We're going to subtract 3 from both sides. X minus 3 equals 2y. And then divide everything by 2. So the inverse of this function is y equals x divided by 2 minus 3/2. And if we take the derivative, so over here we're going to take the derivative of y equals x over 2 minus 3/2. All right, so derivative of y is dy dx. And the derivative of x over 2 minus 3/2, or x halves, is going to be 1/2. And notice that's the very same thing we got when we used that property. So the reciprocal of the derivative is the derivative of the inverse, right? Something to remember, all right? So now, and then at the bottom here, just an example property of the inverse. I'm just actually demonstrating this up here. All right, so just a little show you the inverse here. All right, so if we have, and I'm going to use that with this function here. All right, so we're going to plug the inverse in for x. All right, so we have f, what do I want to plug in? Yeah, f inverse of x equals, all right, so we have, this is our function, 2x plus 3, so that would be 2 times, and our x is going to be, we're going to substitute this for x, so it's going to be x over 2, x halves minus 3/2, and then plus 3. All right, if we distribute the 2, that's going to leave us x minus 3 plus 3. And x minus 3 plus 3 is just x. So you see the function and its inverse cancel each other out and leave only the x behind. And that property, let's see if I can move this up a little bit. There we go. That property is what allows us to find the derivative of an inverse function. It's a good thing that property exists. Let's look at this one. This one's already done for you. what's the value of f inverse of x when x equals 3? All right, so since f of 2 equals 3, then f inverse of 3 equals 2. X and y switch. So interchange x and y. And now we can find the derivative when x is 3. All right, so we're going to use the property. The derivative of the inverse is going to be 1 over the derivative evaluated at the inverse. All right, so we're going to substitute 3 for x, because x is going to be 3. F inverse of 3 is 2, and 1 over f prime of 2, our function is up there, it's 1/4 x cubed plus x minus 1. Use the power rule, so the 3 is multiplied by the 1/4, so that's 3/4. Reduce the exponent by 1, so 3/4 x squared plus 1 is the derivative. All right, and so you're simply going to have 1 over the value of the derivative evaluated at 2. All right, and if we evaluate the derivative at 2, we get 4, so our derivative is going to be 1/4. All right, so this one was just solved for you, and make sure you plug in 2, not 3. So it's the y value is plugged in because x and y are switched. All right, so given to the right is a table of values for f, g, f prime, and g prime. Use the values in the table to find each indicated value in the boxes below. All right, so we're going to be using the property that we just learned. All right, so we have f inverse of 3 prime, that's equal to, and I guess I'll write it like they did, is equal to 1 over f prime evaluated at the inverse of 3. All right, so now we got to simplify this. All right, so now if we look at our original function here, notice that f of 1 is 3. Therefore, f inverse of 3 is 1. All right, so this would be the y value. This would be the, for the inverse, for the original function, that was the y value. This is going to be the x value for the inverse. This is the y value for the inverse. All right, so now this f inverse of 3 is now 1. We're now finding the derivative at 1. Right, so we have to find it at the value of the inverse. All right, so now if we look, f inverse of 1 is equal to 2. Excuse me, not f inverse of 1. F prime of 1 is equal to 2. Therefore, our final answer is 1/2. Let me not mix up inverse and actually I'll put the inverse and prime. So hopefully I won't say inverse when I mean prime, and I won't say prime when I mean inverse. There we go. Lots of symbols to deal with. All right, let's look at the next one. All right, so g inverse of -2, the derivative of g inverse at -2 is equal to 1 over g prime g inverse of -2. Right? So now let's look at, here's where the value of g is -2. So g of 1 equals -2. Therefore, g prime of -2 equals 1. There it goes. Everything is paused. Even my video is paused for a second. Equals 1 over, oh, come on. First, there we go. G prime of, all right, so g prime of -2 is 1. All All right, so now g prime of 1 is equal to 1. So this is just going to be 1 over 1, or 1. So the derivative of the inverse when x is 2 is equal to 1. All right? And that's all you have to do it. So you just got to kind of be careful, slow yourself down. The math isn't hard. It's just you don't want to make mistakes with which point you're plugging in. All right, so now let's find a derivative without using a table. All right, so we want to find the tangent line at the point 4, 2 for the graph of f inverse if f of x equals x cubed plus 2x minus 8. All right, so we got to find the derivative first. All right, so f, actually let me write in a different color so it doesn't blend into my steps. If my steps aren't clear, I'm going to erase them and rewrite them nicer. So f prime, actually I'll write f of x first. F of x equals x cubed plus 2x minus 8. The derivative of that is 3x squared plus 2. The derivative of the inverse, right, is going to be 1. So the derivative of the inverse, there we go, of x is going to be equal to, now, and we're evaluating it at, remember to switch the f, and x is 2, y is on the inverse, so when this is going to be the x and this is going to be the y. Actually, let me make this clear. Whoops, all right, well, I guess that's stuck in there. I'll write it over here. So if f of 4 equals 2, f inverse of 2 equals 4, okay? So now this is, while we can evaluate the derivative, this is not necessarily the actual derivative. It allows you just to evaluate the derivative. All right, so I'll write it in, but usually we think of it as evaluating rather than like this is our derivative. We usually are just evaluated at that point. All right, so f inverse of x, and actually I'm looking for f inverse of 2. Right, because I decided to reverse it. That's going to be equal to 1 over 3 times 2 squared plus 2. All right, so x and y are switched. So if we're dealing with the inverse, right, we want to make sure we use the correct x values. In this case, our point is not 4, 2. Our point is 2, 4. Okay. And I think I'm going to get rid of that just to make sure that that's clear. I think I could have said that clear. So I'll leave this up here, the red. Apparently, some is still left behind. Okay. All right, so the derivative of our inverse at 2 is going to be this value here. All right, so now we have f inverse of the derivative of the inverse at 2. The derivative of the inverse is going to be 1 over, so that's going to be 4, 12 plus 2, 1 over 16. All right, so 1 over 16 is going to be our slope. All right, so this is the slope of the tangent line. and that's for the inverse. The point that we're going to use is, of course, is 2, 4. All right, so that means our equation of the tangent line is going to be y minus 4 equals 1/16 x minus 2, or y equals 1/16 x minus 2 plus 4. Right? And there we go. And we could find that if you ever got stuck, you could always find the inverse and then take the derivative of the inverse, but this is a little shortcut for you. Let's do another one. All right, so here we want to find the equation of the tangent line to the inverse at the given point. All right, so we have, the derivative of the inverse, I'll put it over here, all right, is going to be equal to 1 over the derivative of the derivative of the function evaluated at the inverse. All right, so now we have if f of and I don't know if this was the point for the inverse or the point for the original function. Erase this. So find the equation of the tangent line to the inverse at the given point. So I don't know if that's f of 1 equals 10 and f of 10 equals 1. The question's not clear enough. That's what I have written down, so let's go with that. So hopefully your question will be much clearer. To the inverse at the given point. I don't know if that's the point on the inverse or the point on the function. So if it's the point on the inverse, then the point on the original function would be f of 1 equals 10. We'll just go with it. That's the point on the inverse. All right, so we're plugging in 10 for x. Right? So we have and if this is a point on the inverse, right, then when we plug in 10, we get 1. If it was a point on the function, when we plug in 1, we get 10. So we're just going to make a decision that that's the point on the inverse. So that would be 1 over, so we're going to evaluate the derivative at 1. All right, so that means right, so the derivative, and I wrote down the derivative of the inverse, but we haven't written down the derivative of the function. The derivative of our function there would be 3x squared plus 7x. I'm going to write it to the side so we can just plug in the 1 right here. All right, so now I can just plug in 3 times 1 squared plus 7. All right, so that's going to be 1/10. I think that would be 3 plus 7. All right, so that's the slope. We're asked to find the equation of the tangent line. So that would be y minus 10. Although it would be nicer if it was 10 over 1. If 10 was, oops, what did I do? Y minus 1, excuse me. Y minus 1, reading them backwards, equals 1/10 x minus 10. All right, so this one is really easy to put in a slope-intercept form. Y equals, that would be 1/10 x. That would be minus 1 plus 1. That would just be y equals 1/10 x. All right, let's try the next one. All right, so here the derivative f prime of x equals 5x to the fourth plus 9x squared plus 7. And if that's a point on the derivative, on the inverse, which is not 100% clear, that means that f of 1 equals 13. That would be f inverse of 13 equals 1. All right, we'll go with that being on the inverse. From the statement, the question there, it wasn't quite clear. Same thing on the other one. It wasn't quite clear whether they're giving a point on the inverse or a point on the function. The same thing here. That one may have been the inverse. We'll just make a unilateral decision to call it this, since I already read it. All right, so if you're told the points on the function, then you switch the x and y. If you're told it's on the inverse, then you already have the switched values. Right? I decided that this one would be a point on the function because I wanted to go over the switching x and y. This one will just be points on the inverse. All right, so we have the derivative of the inverse is going to be 1 over the derivative of the original function evaluated for the inverse. So that means f inverse of 13 is going to be 1 over f, and we have 13, which becomes 1. So we're just going to evaluate the function at 1. All right, so that would be, and we already have our derivative, so that would be 1 over 5 times 1 to the fourth plus 9 times 1 squared plus 7. So that's going to be 5 plus 9 plus 7, so that'd be 1 over 21. And that means the equation is going to be, squeeze it in here, y minus 1 equals 1 over 21 x minus 13. We won't put this one in point slope form, or in slope-intercept form. So y equals 1 over 21 x minus 13 plus 1. We'll leave it like that. And there we go. Let's do another one. Right? We have these three here. And again, we'll just go